Today I'm going to talk about morphological image processing. So morphological means shape, form, or structure. So these algorithms we'll see are useful for extracting and describing image component regions. They're usually applied to binary or black and white images, although we'll see a little later they can also be extended to grayscale. And they're founded on the notions of set theory. So unlike the other algorithms we've been looking at in this course, which transform images to images, these algorithms are useful for extracting features of images or measurements of image regions. The topics we'll cover are, first we'll start with some set theory concepts, then look at some elementary operations such as dilation, erosion, opening, and closing. Then look at connected component labeling, which is a very important, useful algorithm. And then the next lecture, other morphological algorithms and the extension to grayscale morphology. So first of all, binary images. Where do they come from? Well, we can get them by thresholding, as we've seen before. MATLAB actually has a function called im to bw, image to black and white, which does thresholding. A little bit later in the course we'll see how to select the threshold value automatically. Another way binary images can come from is a result of feature detectors. For example, the normalized cross correlation produces a score image that you can threshold, and then those peaks represent the locations of detected templates. So for example, if we have a two-dimensional image, a two-dimensional scene such as this, we might want to measure the shape or count the shape of 2D image regions. Lots of applications for this. Here's some: objects on a conveyor belt, characters in a scan document, fingerprints, circuit boards, etc. So first let's look at some set theory concepts. So if we're going to treat our 2D binary images as a set of points, so we have XY points that make up the set like this, and we're going to look at only those points where the image value equals 1. So the set A is not really an image, it's sort of a collection of points like this. And the notation we use is this set notation, which says A is the set, that's the curly brackets, of these elements. Vertical bar means such that, and then I of xy equals 1. Another concept is the union. So the union of two sets A and B are the elements that belong to A or B or both, and we use this symbol to denote the union. Intersection is the set of elements that belong to both A and B, and we use this symbol. And finally, when we say W is an element of set A, we use this symbol here. Another one is the complement. So the complement of a set is all the elements that are not equal to the set. So basically all W's such that W is not an element of A. The set difference of two sets A and B is the set of elements belonging to A but not to B. So it's all the W's such that W is an element of A, and that's what the comma means, W is not an element of B. And then the subset is we write that every element of A is also in B. We denote like this. And finally, the empty set is the set of no elements and has this symbol here. So pictorially, we can still draw these things, even though I said that a set is really just some collection, just a bag of points like this. If I draw those points in a two-dimensional region like this, so let's say this is the set A, all the XY points in this region. Here's the set B, all the XY points that are in here. So the union of A and B is shown here. The intersection is this region here. The complement of A is all the gray area outside A. And the set difference of A minus B is this region here. It's all the elements of A that are not also in B. A couple more concepts we'll need is reflection. So reflection of a set B, denoted by this up arrow, is elements W such that W is equal to minus B for some B as an element of the set B. So basically we are reflecting or negating these vectors, flipping it around the origin, so to speak. So if this is our set B, here's the origin, the reflected set is up here. The translation is denoted like this with the subscript Z. So this says that it's the element C such that C is equal to B plus Z. So basically we are taking every element of B and adding an offset, a translation Z to it. So if this is our set B, this would be the translation of B by some vector Z. So in morphological image processing, we often use structuring elements. Structuring element is just another set or subimage that we use to probe for structure. So these are examples of structuring elements. They're usually small like this. And implementation-wise, we would store these in a rectangular array where the gray areas indicate ones and the white areas would be elements where there's zeros. Oh, we also need to define for each structuring element what its center is. So the black dot here denotes the center. Okay, so the first simple morphological algorithm we'll talk about is erosion. So erosion of a set A by some other set, namely a structuring element B, is defined as this equation. So it says that A eroded by B is all elements Z such that if we translated B by that offset Z, it's entirely within A. It's a subset of A. Namely, we shift B by Z. If that shifted B is completely inside A, we output a 1 at that location. So let's do an example here. So let's say we have this set A consisting of these 1s. Everywhere else we have zeros. We have a set B here, a structuring element, where the origin is indicated by the heavy outline. So what we want to do then is shift B all over the set A. So, for example, I'll put B here. And I ask, is it completely inside A? No. So I output 0 there at the origin of B. So no matter where I shift B along this top row, obviously I'm going to get zeros. It doesn't completely fall inside A. When I put B here on the second row, now that location is completely inside A, so I output a 1. And similarly, every other place along this row is also completely inside A. With the exception, I guess, of the last position where it goes outside the set A. So if I assume there's a 0 there, then that would be a 0 output. The rest of the rows are also zeros because there's no way that I can shift B so as to output a 1 completely inside A. So that would be the erosion of A by B. Okay, so another set of examples, we'll use different way to display that is using these gray areas. So imagine that set A is a collection of points in the square here. My structuring element B is just a little square of size W by W with the origin in the middle. So the erosion of A by B is just this darker gray area inside the original large area. So that's because only those places that are completely inside the original area. For example, this location of this square is completely inside the original set A, so I can output a 1 there. But if I go any further outside, away from the center, I have to output a 0. I can also use a disk structuring element of radius r, which turns out I get the same result for the erosion of A by B. Namely, it's smaller by, in this case, the radius r. If I take a structuring element that has the origin not in the center, but say in the corner here, then this is the result of erosion of A by B. Remember that I have to output a 1 whenever the structuring element is completely inside A. So that's true at this location, but if I go any further outside there, it would not be true. So in general, we can think of erosion as shrinking a region. So it makes a region smaller, it makes holes bigger, and it makes any thin parts, it makes them go away. It's not commutative. And here's an example on an image. Here's my original image. Here is the result of eroding by a structuring element of size 11 by 11. So these thin lines are smaller than 11 by 11, so they disappear, and everything else shrinks. Using a larger structuring element, I even get rid of the thick lines, and even larger structuring element, I get rid of all this stuff on the outside. So it destroys anything smaller than the structuring element. Okay, let's look at the opposite of erosion, which is dilation. So the dilation of a set A by a structuring element B is defined this way. So it says that we want all points Z such that we take the reflected B, offset it by Z, and if that intersects A at all, in other words, the intersection is not empty, then that point is in the dilation. So effectively, we reflect B, we shift it by Z. If it overlaps at all with A, we output a 1 at the center of B. So let's look at this example. Here is set A. Here is my structuring element B with the origin here. First thing I do is reflect it. So now the origin is over here. Okay, so again, I slide it all over A, the shifted version of B. So the first position, for example, would be here, where that's the center. Does it intersect A at all? No. So I output a 0. So obviously I get zeros everywhere in that first row. Only when I get to this point do I output a 1. And I also output a 1 here at that location, and when B is in that location. So I get 3 1s on that row. Third row, I would get a 1 here and here. The next row, I would get 1s here. And the last row, here and here. So that is the result. Everywhere else where I haven't drawn is a 0. Another example, a little bit more complicated structuring element. We reflect B. So the reflected version of B is this, where this is the center. Sliding it over. One thing you'll notice is that obviously I get the original points as part of the dilation because the origin of the reflected B is also a 1. So I definitely know the original points are still in there. But I also get a number of additional points. For example, I get this point because the reflected B is overlapping A right there. So I'll get this point and this one, and then those as well.